have hello in the future from the past. It's awesome.
Hello.
Everybody, we got a couple rules in the chat here. 1, if you got questions, put them into the Q&A. 2, light up the chat. It's very difficult to present to nothing except a blank camera. And 3, always bring PMA. Christina, what's PMA? Positive mental attitude. That's right. Okay.
Yes.
So everybody, light up chat. Tell us where you're coming in from today. It is December 10th, 2024. Hello from South Africa. Hello to South Africa. Everybody, great to see you. Have a seat, grab a chair, sit wherever you'd like. Today, we got quite a show for you. But first, before we kick things off, we interrupt this Tradecraft Tuesday to bring you a special bulletin. Huntress, we had kind of a crazy night last night. I don't know if anybody's seen anything from our social media postings on this, but we have uncovered, in response to exploitation we saw across the Clio software suite. That's CLEO, not CLIO. The Clio software suite. Our SOC, our Australian Night Crew SOC, over the weekend found a bunch of post-exploitation activity surrounding this type of software. And we started to peel back the onion. And the more we peeled it back, the more we started to cry. So we wrote up a threat advisory on it. We accidentally stumbled across an additional 0-day in addition to the one that was patched back in October. It's a whole mess, but go ahead. Here is, actually, that's not the link. That's the link to the YouTube broadcast we're on right now. And if I gave you that, that wouldn't make any sense. Thank you, Christina. Check that out. That's our blog on the subject. It's crazy, but check it out later because you're here for this Tradecraft Tuesday. So check that one out later. But anyway, we return to our regularly scheduled program. Christina, you feel ready? What do you think?
Yeah, let's do this.
Okay. So let's wind it back. I got a little story to tell before we kick off Tradecraft Tuesday. October 11th, 2024, precisely 1 week before Christina and I step on stage at B-Sides New York City to present findings for the research project that you're about to see. Somewhere deep in the vicinity, buried in the snows of the Huntress Research Facility, we had been staring at this graph for weeks now, and you're probably looking at this and you're like, oh, that's pretty. Are these like constellations or something? No, you will understand what these nodes and what this graph depicts here in a moment. But we saw one thing in particular that made us freak out. All right, so let's zoom in, enhance, right? So we, after a lot of back and forth and combing through all these nodes and running Python scripts and crunching numbers and looking at all manner of attributes of these nodes, we found this, right? And the 4 rectangles, the 4 red squares that you see on here made us go like this, all right? So that's me, that's Christina, and a few other researchers in the room at the time. And again, you may not understand what's going on here right now, but let me break it down for you, because those 4 squares indicated, we looked at the data that is the underlying kind of data that's represented in graph form in that picture. And we saw this. This is the representation of an M365 tenant that Huntress protects, but in this case, just an M365 tenant that has an application installed, right? That application is named ... 8 dots. Okay. That application, that OAuth application in that tenant, had a credential object. That credential object was called ... 5 dots. Okay. And the app itself, and again, what does this all mean? We'll get there in a moment. The app itself had the OAuth consented permissions to access a user's mailbox, or really access the mailbox contents of a particular user in this tenant. The user itself is the lighter blue node with the name blurred out, and the app role assigned to value in this case just means that that user was using this particular app. They were the one that installed it and consented to it. And that means when we crunched all the numbers and looked at this, this was proof of our hypothesis that we set out to look at when we decided to start looking at all this data in our tenants. That is evidence of Azure application attacks in the small to medium business ecosystem. So we had a hypothesis that we'd be able to find hackers using evil applications, installing custom evil applications, but we had no hard evidence until we saw this graph right here, right? So after we had gotten back into our chairs, after falling out of our chairs, we started to talk about it. We were very excited, but it kind of made us think at this point, how many more are out there, right? Because we found a few examples. we found examples of hackers installing malicious applications in our protected tenant partner data set, but there must be more out there. If this is a favored technique, tactic, and procedure by hackers, there absolutely must be more out there. And so with no further ado, with the storytelling out of the way, Christina and I are proud to present When Apps Attack, our Tradecraft Tuesday presentation, hunting Traitorware and rogue Microsoft 365 apps at the small to medium business scale. My name is Matt Kiley. I'm one of the principal security researchers at Huntress, and I'm joined today by my esteemed colleague and co-host, and probably the reason that this project succeeded despite my best efforts to sabotage it, Christina Perry. Christina, please introduce yourself.
Hello, and thank you for the intro, Matt. My name is Christina Perry, and I am a staff DevOps developer at Huntress. And yeah, super happy to be here and talk about rogue apps and some of our findings today and the brain power behind it.
So here's our agenda today. Our agenda for today, we'll split it right in half. I'm going to take the first part of this presentation and talk a little bit about the tradecraft of OAuth applications in M365. Really can be broadly kind of applied to the entire area, the attack surface of OAuth applications in identity platforms. I will talk a little bit about the two different specific types of tradecraft that we were looking to hunt, how they work kind of in a test tube. But then I'm going to turn it over to Christina, and we're going to talk about our hypotheses, our research methods, and our findings for when we took the Huntress data, the partner tenant sets as a data set and started to look through and come up with hypotheses and data science approaches and all kinds of crazy stuff that led to finding the findings that we covered in the little stinger storyteller intro of this one. So let's kick it. So before we talk about the tradecraft associated with applications, we need to understand a little bit about why OAuth applications have associated attack surfaces and what hackers can do with them in the right context and circumstances. So settle down, kids. It's time to talk about OAuth. Here we go. Here's an Azure application crash course. If you're familiar with this, this may be a review for you, but if you've never really thought about popping the hood of Azure and understanding what it means to actually install an application, well, this is our time. So show of hands or put a 1 in the chat if you've ever seen something that looks like this. So this is, and don't worry about the actual application name here, but just if you've ever seen this window before and you've ever had to either request approval, or it might say consent or yes, or it might even say consent to for your entire organization in some cases. This is the user experience associated with Azure application, OAuth application installation, right? So if you want to, that's a lot of yeses, man. That's a lot of yeses. Good. So most of you are at least familiar with what this looks like when you're kind of interacting with it, right? But so this is what it looks like when you interact and install applications in your M365 tenant, right? So Azure wants it to be very kind of an attractive option for developers to build their applications in the cloud, host them in Azure, and then have other people use them. And when we say applications, this can literally be anything. It's up to the developers to build whatever kind of applications that they want and then host them in Azure. So these apps do all kinds of things. There are apps that organize your calendar. There are apps that organize your Teams messages. There are apps that hook into other resources that use the identity provider of Azure to authenticate to those other resources. So it's just like databases, internal employee apps, line of business apps, a single tenant app or a multi-tenant app. It's just apps, right? So it's the ecosystem by which you can build these applications. And it is built on a very opinionated and weird, may I add, in my humble opinion, OAuth 2 implementation, right? Azure implements OAuth 2 as the authentication backbone. So Entra ID really is the authentication backbone using OAuth 2 to facilitate the authentication and authorization of these apps. It's a little bit like Kerberos for the cloud. If that means something to you, then you might appreciate that. I don't say that as a compliment. If you are unsure what Kerberos is, again, don't worry about it. We're going to go into what this actually looks like here in a moment. So let's talk about what this looks like from an actual use case perspective, because I think that's kind of in the benign, legitimate use case. This is kind of what this looks like, right? So you start with the end user, because the end user is always where you're going to start with something like this. And let's say there's an application out there that the end user wants to use, right? They live in, let's call it the HuskyWorks Azure tenant, right? So Entra ID in the HuskyWorks tenant accounts for their identity and their authentication. But the SumCorp Azure tenant is where this application is actually built. The maintainers, the developers live in the SumCorp Azure tenants, and they've published their app as a multi-tenant app, so anybody can install it. First thing the user's going to do, if they say they want to install this app, ooh, this is cool. It's going to be like a little calendar application that can organize my calendar invites or something. They're going to go to wherever that is. Sometimes this is a client application, so you download software. And then to hook that software into your Azure tenant, you're going to say, hello, I would like to install this application. So the application is going to say something like, hi, I'm Email Buddy. I can help you track and organize and back up your emails. To do this, you need to, one, install me in your tenant. Consent to the permissions that I need to access your email, and then authenticate your identity so that everybody knows that you were the one that actually installed this and are using this, right? And by the way, I use the Graph API. I use an external resource to do this. So you have to basically tell the Graph API through Entra that I am okay to access these resources on your behalf, right? So the application at that point, after authorization, will say, do you consent to the following? And that's where that little box comes up, that little screen that says, this app is going to need all the following permissions, right? And at this point, and by the way, the mail.readwrite, mail.send, those right there are Azure's implementation of OAuth consent grants permissions, right? So the actual thing that says that you can access somebody's mailbox or their mailbox settings or their calendar, that is kept track of by this permission grant. So the end user says, yep, and authorization and authentication happens. So they say, I am the user that I say that I am. I'm going to go ahead and install this in the tenant, and I'm going to consent to this app having access to those particular resources on my behalf, right? And the application then installs what's known as a service principal in the user's tenant, the end user's tenant, right? What is a service principal? Well, you can think of a service principal kind of like a local installation service account for that application. So it says, greetings, because it's a robot. I'm an instance of Email Buddy. I'm not the actual application. The application over in the SumCorp tenant is like a blueprint. I am the actual, the gears turning that actually allows you to use this application. So I'm going to go ahead and get installed in your tenant because you authorized me to access resources on your behalf, right? And now, at that point, the app is authenticated because somebody said, I'm going to go ahead and punch in my credentials and say, let's go ahead and install this in my tenant. It's authorized. I consent to you having access to my inbox and my emails and my mailbox settings. And you can call the Graph API to be able to read all of that or manipulate it however the app was designed, right? When the user wants to actually use this, if they have that client application, they may go to Entra and say, hey, can I use this? And Entra, the local instance, the authentication backbone of that tenant, will say, yep, you are authorized. You're the app role assigned to user of this application. You are authorized to call the Graph API with these following permissions, or really you've authorized the application to do that on your behalf. And the service principal says affirmative because it's a robot. And Entra, in that case, gives you a token. And what can you do with this token? You can use that token to call the resource that the app was designed to call, right? So at the end of the day, you authenticate in your local tenant, and through the magic of OAuth, that application now has a token that you can cash in for an actual type of data, a resource, something like that, right? And all is right in the world. If that is the legitimate use of these apps, that is how that goes. And if the app is built in-house, if this is like a line of business app, it's not from some other tenant where some other developers have developed it. It's basically the same process, except everything happens intra-tenant, right? So the installation, you look at the application itself, a service principal of that application is already there in the tenant itself. You consent to it, authorization and authentication happens, and then token is exchanged, and then that token, again, can be used to call the graph, right? So too long didn't read. Almost the exact same kind of steps, but it's just, it all happens inside of the tenant. If you're the one that has developed this application and built it in your tenant, that's going to be important. There's a quiz on this later, so I hope you're paying attention, right? Now, what's the quiz on this later? The quiz is that notice how this entire ecosystem has a couple of very interesting attributes to it, right? Apps can be built in-house or they can be installed from somewhere else, right? It uses OAuth for the authentication and authorization. You know, which tenant am I authorized to act in, and what accesses do I have? What resource do I have access to? And you can set it up so the application is delegated access from a given user, right? So the user will install and then say, I I authenticate and I consent for this application to access resources on my behalf, right? And like every good kind of complicated, weird implementation of some kind of authentication schema, this, of course, makes it a fantastic ecosystem for exploitation. I said Kerberos for the cloud, and that wasn't a compliment. This is why I say Kerberos for the cloud. So attackers can then either build apps in their own tenants or socially engineer somebody to install an app or install one after initial compromise, like initial access. It's built on the system of authentication and authorization that's built into Entra and Azure, right? So this is the best exploits in the world are features, not bugs. They're things that cannot be patched out, right? So that, like I said, Kerberos for the cloud, Kerberos exploitation happens because of the system, not necessarily any flaws in the system, but just how the system is built. This is exactly the same. And it can be scoped. You have a lot of customizability as a hacker in this case. As an attacker, you can scope the app to the types of permissions that you need. Single user access, multi-user access, if you have the right permissions for that. So it's really the sky's the limit. And it's like, how creative can you be in the design of an application if you can install it after initial access or get somebody to install it on your behalf? Great system for exploitation. And this is why I say that Azure applications, I think, Entra applications, and OAuth apps in general are, I think, the most underrated form of exploits, initial access, and persistence in the identity space in M365. Because there's lots of customizability, and I don't think it's well understood that these are kind of an attack vector, right? So let's get specific, right? Let's talk about two interesting specific attack Tradecraft use cases. First is what we internal to Huntress have been nicknaming Traitorware. In the summary of Traitorware, you can think of this as every app has a dark side, right? So Traitorware is OAuth application abuse in M365, where the app was not specifically built to be evil. So there's kind of like an intention aspect of this, right? The closest approximation that I think we have is like a bring your own RMM or like bring your own X or like a lol bins kind of. A lot of these are not like present in tenants by default. So there's not really a lol bins. There's not really anything to live off the land. You kind of have to bring your own land, I guess, if you really want to get the metaphors mixed up. But the closest approximation here, this is like bring your own X, bring your own fill in the blank. So the crux of the interesting part here is that anything the app was designed to do, if these are air quotes legitimate applications, so we'll point to a very specific example here, EM clients. If you spent a little bit of time around IR in the identity space, especially in M365, you probably have seen this before. This is a legitimate application. It's you can go to the website. This is not malware, right? This is an application that hooks into someone's inbox, right? And it organizes your inbox. It can organize multiple accounts inside of the same inbox client. But the idea is that, like, even though this is air quotes a legitimate application, right, with legitimate use cases, the structure of this app, what it allows you to do, is so useful to attackers that it's absolutely absurd, right? So you authenticate, you sign in. So this is me signing in with my global admin. So like in a nightmare scenario, this is me signing in with my global admin account, right? You consent. We remember this, right? You consent to the permissions for this application. And this is delegating access to the application based on the authentication credentials that you just provided. In this case, for this screenshot, this is my global admin user, right? And like I said, you can tick that little consent on behalf of your organization if you really want to have a field day with this one. But then you accept. And then at that point, in the legitimate use case, your user would just be using EM clients to access their inbox, right? And that's calling the Graph API. And I think another resource, I think possibly the O365 management API to do that. But beside the point, you cash in that token, you get some kind of access back, right? But in this case, it's not the actual user, it's the hacker, right? So this is post-exploitation. It requires some kind of initial access, but after you've secured initial access, install EM client, you get to organize all of your mailboxes that you've compromised in one email client. That's why it's so useful, right? So that is good apps gone bad, I guess, if you want to look at it that way. So let's talk about bad Apple apps, right? So this is the second type of tradecraft that we'll cover here, these are artisanal, handcrafted, farm-to-table evil applications. So this is OAuth app attacks. The long form description of this is OAuth consent grant application attacks, but that's like scientific nomenclature, and ain't nobody got time for that. So this is like if Traitorware, if the thing we just covered were like, good apps gone bad, the living off the land or bring your own or something. This is like custom written malware, right? So the attacker in this case creates applications that are specifically designed for persistence or initial access and attack development, right? So there is no legitimate use for these applications. So this is like they're trying to hide, random characters.exe in the process list or something like that. Like this is like a custom written piece of software that's designed for particularly attacks and evil and that kind of thing. And no two of these are going to really be alike, right? So like the permission scopes might be similar if they're built to access somebody's inbox by calling the Graph API. Some of the permissions are going to look kind of same, but the names aren't going to be the same. The publisher, if that detail even exists, is not going to be the same. So these are very customizable. Microsoft recently tried to nerf this. By nerf, I mean like remove the power of this kind of thing by specifying only verified publishers can have access to these certain types of permissions. But like all kind of countermeasures like that, it just becomes a cat and mouse game. So these are still very powerful, right? So want to see how to build one? So all you really need to do, and again, this is just like using the system as designed, feature not a bug. All you have to do is register an application that you would ostensibly be developing somewhere, right? But you just build this in a tenant, right? There's nothing special to this, right? If you already have access, you can make a single tenant application that is just based for persistence, right? So that would be how you do that. Or if you're trying to pivot this for initial access in some kind of social engineering attack, you would make it multi-tenant, right? So you'd install it in your maybe sock puppet attacker tenant and then email somebody the consent link for this one, right? So this is why these apps are so powerful, because you then as an attacker get to say like, what do I need to persist or collect info or steal somebody's mailbox or stage a business email compromise, financial fraud attack or something like that. And like the most common Microsoft API is definitely the Graph, right? But there are lots of other resources that you can build this to access. You then just go ham with the permissions, right? Like if you need access to somebody's mailbox settings, like tick that box, right? If you need access to somebody's mailbox itself, tick that box. Some of these require admin consent. Some of them require admin permissions in the tenant. But again, if you have that, this is a really good way of persistence. And then beyond initial access, on the subject of persistence, we're going to look at maybe just one of the two here. There are two tactics that I see that are super interesting. One of them is you just set up an OAuth authentication endpoint. You can specify that while you're making the app. You punch in a URL that says, oh yeah, go ahead and send the token once it's authenticated to this URL. That URL happens to be like an attacker listener. It's just a URL that the attacker controls. And then an access token and a refresh token for those app permissions gets sent to that URL, right? The more interesting one, I think, is this one, backdooring a service principal with a permission. So remember, our service principals are like little robo guys. They're little robots. They're little local instances of the application. Well, that's really just an account, right? In the OAuth schema, that's an account, and you can set up that account to have a one-factor password that you can use to authenticate yourself as that service principal. And that's how you kind of set it up. So you punch in a client secret. That's in the beginning of this presentation. I pointed out the two apps that we found had client secrets attached to them, right? This is exactly what's going on there. You punch in the client secret and you copy down this value right here. And that's it's like a 30 character long random password, right? But at that point, if you have the password, if it's just an account, if a service principal is just an account and you have the password to that, you can use something like the Azure command line utility to just log in as that service principal, right? You give it the password, you say the ID of the service principal, and then you're in. And you get to now play the role of that app because you have authenticated as that app. So if the app was built to call the Graph to return somebody's, get a user list or get somebody's mailbox, their emails or something like that, you get to just do that, right? So I grab a token here in the headers equals authorization bearer equals token. That is just, I've authenticated in this one right here. I authenticated as the service principal to the Graph API. I take a token, I cache in that token for any type of information. Enumerate a user's inbox rules. If you want to stage an inbox rule for business email compromise, that's a good time to do so. So yeah, you get the idea, right? Service principal sign-ons are not subject to conditional access rules either. Yes, I don't know the answer to that, and I don't want to give you a bad answer to that, so I need to look that up. I'm not sure. So in summary, OAuth apps used for initial access, persistence, furthering the development of attacks. Apps are customizable. They can be persistent. They're usually flying under the radar. Some of them are like Among Us, right? It's just it's an imposter app. It's an evil app that's been built for evil and is blending in. Some of them are a little bit like a crowbar, right? Like you can't just say everybody that owns a crowbar is a criminal. Like some people need to open a bunch of boxes, right? But like if you see somebody like at a window using a crowbar and they're wearing like a ski mask or something, like you might think twice about what that person's intentions are, right? So that's the summary right now. That's the tradecraft. That's a little bit of the approach. That's a little bit about how OAuth apps interact in this ecosystem. So I'm going to turn it over to my esteemed colleague, Christina, because when I started thinking about where I wanted to take this research, I needed somebody with a lot of like data science, brought that experience to this project, built an entire scaffolding, came up with the research methods, came up with the methodology of testing our hypotheses. And between her and I, we enumerated a 2,600 tenant data set from Huntress to study all of this at scale, right? So Christina, without further ado, kick it over to you. Take it home. And you're muted, I believe.
Thank you. That would have been embarrassing. So let's jump into it. 1 second. Okay. So yeah, thanks, Matt, again, for giving the background on Traitorware, OAuth app attacks. Now I'm going to talk a bit more about hunting these M365 apps at the SMB or small, medium-sized business scale to level the playing field against threat actors and nefarious users. Okay. Sorry, my setup changed. Oh, there we go. Okay, so what are we looking for? As Matt gave examples of both the types of attacks we're talking about today, Traitorware and OAuth app attacks, we do have a sense of impact, obviously, to get persistence and attack vectors. Why do we care? We know what threats lurk out there in the Azure ecosystem. And to what Matt was saying before, there was a figure I found online, and it was about 20% of all categorized threats in the identity Azure space relate to OAuth apps. So it really is something that's becoming more and more on the forefront in terms of attacks that kind of been under the radar for some time. For those, so at its worst, it can allow attackers the ability to abuse existing apps with the right permissions, crafting new applications in a credible tenant and obviously be able to gain persistence into the environment. And this is just one example of the broader impact that we can see at the SMB scale, but I'm going to hone in a bit more on how we can identify Traitorware and OAuth app attacks lurking in the wild. Okay, so to kind of peel back like the onion layers on this, we built a proof of concept around how we can try to answer the question, how do we find these out in the wild? We have a few ideas and potential red flags in terms of things to look out for. First, we have prevalence. What are the most and least common apps that we see? Are there some commonalities perhaps in the things we see? Do we need to take into account, like Matt said, unverified publisher domains? Maybe does it need to be verified? Are there any other particular patterns that stand out to us? Next, we have application permissions and scopes. We would like to identify first which apps have the most powerful permissions, and secondly, where do we see those apps with those permissions? And then lastly, we have user persistence. So what's the potential attack surface? How can these permissions enable persistence for the user? And these are just kind of things to keep in mind. This was kind of our hypothesis going into our proof of concept for things we were hoping to find, looking to find. So pause on this for a sec. Okay, so a bit of background. I feel like I don't really have to go in detail too much here since Matt did a great job of like explaining the different types of apps. But in terms of the data that we're using for the proof of concept, if you're not familiar with Graph API, basically has a bunch of information on users, application service principals, tenants, and those respective relationships, as well as permission scopes and grants. So by having this data and being able to tie together these relationships, we're able to get a sense of, okay, like in the beginning of Tradecraft Tuesday, where Matt gave an example of the nodes that we had, being able to call out what user has certain permissions and maybe they don't need to have those. So by having access to this data, we're able to call out those abnormalities in the data. But taking that a step further, how actually are we going to analyze and visualize this data? For a proof of concept, we used Elasticsearch as well as Neo4j, hence the lovely graph images you see throughout here. Elasticsearch we used for easily querying and filtering for the data that we have based on the different types of relationships at a user, application, service principal, and permissions level. This is able to help us answer questions such as prevalence and maybe what are the most and least common apps seen. And if we wanted to do any additional pivoting, Elasticsearch is great for that. When it comes to Neo4j, again, it's self-explanatory. It's to visualize relationships between all these different entities in a graph format. And yeah, and basically being able to call out things that might not look what we'd expect or anything that stands out. So how did we implement this? Hold on a sec. Okay, so in terms of the development plan for this, pretty straightforward. First, we had to get the data, which required getting access to the Graph API via token. And David Atland in our team at Huntress is able to help get us set up with getting data pulled from the Graph API. Then
Thank you, Dave.
Thank you, Dave.
Thanks for that.
And he was able to help us out with that. And once we have that data, so that we're not querying and enumerating over and over again, we want to be able to cache this data. We use AWS for storage for scoping this out, and then bulk ingesting the latest into Elasticsearch. So for the purposes of this proof of concept, we had about 2 gigabytes worth of data, about 1.8 million documents, and then basically getting this data as well into Neo4j for representing it. And we also had like a side-loaded script, if you will, for creating zip file and doing like one-off analysis just for checking like prevalence and getting some quick stats via Python utility. So that was also very helpful. But yeah, and like I said, for the case of this POC, we ran it on about 2,500 tenants. So that's about 10% of the total Azure tenants that like Huntress has. So yeah, this was just kind of like see like what are the weird things lurking out there, and this was kind of the starting point for delving into that. So the implementation, as I mentioned before, we did use AWS for infrastructure, and in terms of what we used, we had 2 EC2 instances. One for basically being the data collector via the Graph API. This was just a Python script, grabbing all the data, having somewhere to send it to, upload it to S3, cache that. And then we had a second EC2 container for running the services. So we had Docker containers for running the Elk stack and Neo4j. And yeah, so, and like I said, we had a compressed capability of just getting everything from S3 into a tarball just for side loading into our ad hoc script for checking prevalence and quick stats. Okay, so implementation, I have 3 different data models for what we're honing in on. And this is basically what the data looks like in Elasticsearch that we're working with from the HuskyWorks tenant. And basically we're using the tenant key. I highlighted these different colors to kind of highlight which fields we have nested and which ones. This is basically how we're able to identify and piece together the relationships between the users, service principals, applications, and permissions. Because if we don't have that, how are we going to be able to tie all these missing pieces together? So we have the tenant ID here, and this is for a user data model. So this maps to a single document in Elasticsearch. And we have the user ID, tenant ID, display name, and user principal name. So when we were wrangling this in Elasticsearch, we could easily query a wildcard search pattern match on any of these fields. And then I think there's more interesting stuff that comes with the data pivots, looking at the application data, because this gives us more information on the name of the application that we have for a given tenant, created date, publisher domain, sign-in audience, password credentials, resource accesses, and OAuth permission scopes. So this is a lot more telling for us, because if we see certain relationships to applications where we wouldn't be expecting something, or there's password credentials that are shared in here that may be able to give the user persistence, then that can be very helpful in this case. Another thing too that I wanted to call out is on the right here is the breakdown of the number of documents that we have in Elasticsearch. So we largely see service principals, and there's honestly relatively few applications and users. And you might be wondering, why is that the case? We are seeing this because we would expect for there to be lots of service principals, i.e. those little like robot guys that Matt was talking about, running for a local machine, versus for users, there's a one-to-many relationship between a user to an application, and then many service principals. Yeah. And then, so what did we find in terms of rogue apps? First, starting with Traitorware, across the 2,500-ish Huntress partner tenants, we found that about 10% of these had at least one rogue app, which is common, which has been observed during the Azure identity attacks. In some cases, we found that one identity from a tenant had many applications. Some have been lurking for quite some time, and we just didn't realize. So what we learned in trying to find Traitorware is it's really a needle in the haystack type of problem for determining sus permissions and scopes and trying to identify how user persistence is obtained. So how I was talking about earlier, that we had a side-loaded Python script for basically generating these tables to summarize the data that we had. We could also do this from Elasticsearch, but this was just a quick way of like eyeballing and giving a 50,000 view of what prevalence we saw in terms of applications and service principals for all the tenants that we saw. So what is this telling us? We see that for the prevalence bracket, so in the 90 to 100%, this is for the most common ones that we are seeing. And a tenant with a lot of service principals is quite common, like I said, because it's that one-to-many relationship. However, there are significantly more service principals and applications unique to each tenant. So when we were crunching these numbers, we found that we had a lot of apps. So 99% of these were apps, and greater than 91% were service principals. So most of these fall into that less than 1% bracket. And what this tells us, this chunk here, is okay, these are the ones that fall into the less than 1% prevalence bracket. This means that they're not common. It means they're highly unique and customized to each local instance where it's running. That's why the number of applications is so high, as well as the service principals. And we would expect that, but like I said, it just leaves more room for OAuth app attacks and nefarious things to occur here. Okay, so more findings. This is going back to prevalence and what are some of maybe the most common M365 apps by tenant. This was obtained just by doing some aggregations on app display name by unique tenants in Elasticsearch. So most of these you'd expect to see like Microsoft, SharePoint, media analysis and transformation, web clients for Teams, because these are Microsoft 365 apps that most folks are going to be using on a day-to-day basis. So we would expect to see these things. And like I said, having a high prevalence probably means they're okay. So
either so like
mhm.
prevalence in the 100% range, we figured, or like really you could apply this to like the upper quartile, almost maybe the upper half. If we assume that any of those apps are not okay, we are fighting a bigger battle than I think any of us are prepared to handle, right? So like all of these apps that we see that were installed in 100% of tenants, you either assume that they're default and probably fine, and they're because Microsoft furnishes them and puts them there, or there's some kind of nefarious activity across 100% of our tenant data sets. And what are we gonna, that's when I walk away at that point. I don't know if I can even do anything about that. So
Yeah. Agreed. So yeah, so being able to find prevalence by most common, definitely helpful for trying to like find like filter out the noise from all of the data that we're looking at. It's pretty safe to say, okay, this is fine. And what else do we have? So like I said, this validates our first hypothesis of prevalence and being able to identify most common ones. Like I said, can largely assume they're Microsoft related and used by and large by most folks, not suspicious. Otherwise, we have bigger problems on our hands. And then for the least common, again, your mileage may vary because like these could be totally innocuous things that like a sysadmin spins up. I'm not necessarily saying that because it's in the less than 1% of prevalence that like it's automatically sus, but it is helpful for trying to, like I said, discern like the noise from things that might actually be suspicious and looking into. So, yeah. And then, secondly, in terms of findings for OAuth app attacks, we are able to fine tune this further. So, you have the needle in a haystack, and we're trying to narrow down here what apps, or sorry, what rare service principles stand out for us. So, the total number of service principles analyzed for this was over 1 million, which is impressive. And then to see that about 1% of them are rare or less prevalent, that really filters down looking for the needle in the haystack. Now we're looking at what was maybe originally a larger data set. We now have a much smaller subset of that to work with, which is a lot more wrangleable. I don't know. So yeah, so let's take that and analyze it further. Basically, we now know for OAuth app attacks that if we want to find apps and service principles, or yeah, principles with the following characteristics: global prevalence of less than 1% in the surveyed tenants, and then specifically when it comes to OAuth scopes that can be abused, we want to look for ones that are high privileges, able to like grant the user means of getting persistence. So some of the common ones that we saw highlighted, and there's various white papers that I've referenced in these slides at the end of various permissions that we see that are quite common to be abused for OAuth apps. So for example, the first example I have is for mailbox settings. That's high privilege and related to phishing. User read write all, never a good thing, especially if it's at like a tenant level, definitely a red flag. And that has broad impact. So that coupled with application read write all, also it's pretty dangerous because when you see this for all principals in the tenant, that means that somebody, whether it's a sysadmin, just permissioning something like a new service principal, or perhaps it's something that is used for nefarious reasons. We want to be able to discern these types of cases where OAuth scopes could be abused. The second example being for service principals containing the permission scopes for directory read write all. Again, like I said, this is also can have a lot of potential damage because it's effectively global tenant admin perms, and they can do whatever. So very dangerous. And just to kind of go into examples of what we have pulled from the data that we have some examples of these where we have cases of read write all permissions and OAuth apps that are doing things that maybe they shouldn't be. So this tells us that between having the collection and all files read, that's suspicious. Having the directory read write, as I'd mentioned, that's also suspicious. And unknown publisher, I feel like it's one of those things that like maybe it's suspicious, but like in this case, like I don't like it's not enough information to really discern that.
I mentioned in the chat of the like 159 service principals that we found across 100% of the tenants. In other words, if you spin up a tenant, there's going to be some defaults there. A good portion of those did not have. There were Microsoft apps, obviously, but they did not have Microsoft as their verified publisher, which is like. So yeah, when we were looking at that one, it's like it's a potential indicator, but it's not very strong because if you're going to tell me that the Microsoft furnished apps also don't have that as the verified publisher, then I can't really use that as a smoking gun, at least.
Mm-hmm. Right. And then for the prevalence percentages here, Matt, remind me what these are.
Sub 1%, right? So we took the just to funnel it all the way down to the extreme rare. We took any service principal that's sub 1% and then started to apply the layers of different permission filters, right? So that prevalence rate is everything like we have, 0.05. I think we truncated it to one decimal, and that's why we've got 0.00. It might be like 0.001 or whatever. But yeah, that's the extreme rare service principals, the things that don't exist like hardly anywhere else.
Yeah, thank you. Yeah, so with knowing that, based on our original hypothesis, were we successful in finding OAuth, app attacks, and Traitorware? Yes. And it turns out that the indicators that we had in mind initially did really come into fruition for being able to refine that needle in a haystack down to a much smaller, stomachable pile of data that we could work with and wrangle, which is awesome. And in terms of, I wish I had more screenshots for the actual like Neo4j side of this, because we really were able to eyeball relationships in our local dev instance of, okay, these are things that are totally suspicious, like the 5 dots and the 8 dots. And then we found some that were like, is this a sysadmin? Or is it something that could be like more questionable than that? And I think this was really just like the tip of the iceberg in finding those relationships. Now that we've set up the methodology of, okay, we're loading all this data into Elasticsearch. We have it in Neo4j to drill down on any more anomalous activities and stuff based on looking at prevalence, maybe application permission scopes that might be a bit higher than what we'd expect. And lastly, for user persistence, being able to identify that, hey, if users have these permissions, like global tenant read-write access, they probably shouldn't have that, and obviously are dangerous if they fall into the wrong hands. So just to kind of recap on like the findings of our POC, it's not a one-size-fits-all approach for finding rogue apps for small and medium-sized businesses, being that apps are widely customized and unique to each tenant. So finding that smaller needle in the haystack for data that's actually interesting, and we want to tease out the apps that actually appear to be malicious, that is the key here. And we've basically determined an approach to find them using prevalence, permission scopes, and identifying where there's user persistence. And again, for when it comes to the permissions and scopes, one of the things that we could do to mitigate this as more of like a takeaway, obviously, I think someone mentioned in the chat, great job, principle of least privilege, so that you can restrict app permissions for users. That's one piece of the pie for making apps safer in M365. And when it comes to user persistence, in terms of more things that could be done here, like maybe you could use risk scoring. I know MITRE has some risk scoring that's open source and available. But I mean, these are just ideas of ways that you can start to disseminate further where these rogue apps are. what characteristics and attributes we can associate with those.
Yep.
So yeah, that's what I wanted to share.
One of our major sources for this was the Microsoft threat hunting documentation. It's like the MSD, and but for applied to threat hunting specifically, they have a whole. I'll just go ahead and grab it and throw it in the chat. They have a whole breakdown of like the methodology of threat hunting in your individual tenants against this kind of stuff. So let me go find that real quick. I'll throw it in the chat when I find it.
Yeah, and I think if I'm not mistaken, that's the same link that you're sharing had examples of the different permission scopes that flags like, hey, these ones are definitely suspicious if you see these by service providers. I think when we share out the slides for this after, there's like a ton of like awesome white papers that are out there from like Rockstar and 365 security researcher folks being like, hey, these are like the Microsoft ones that Matt's talking about. And then wait, there's even more of those out there. So it's really becoming more of a science to see that there's a lot more discerning to what could potentially be rogue apps out there. Yeah, so that's really the recap on this. But wait, there's more. So as a takeaway for y'all, what should you do if you see rogue apps in the wild? So fear not. This is born out of this project, the POC for finding rogue apps. We have a repo for rogue apps where we can find any apps. And basically, this is to crowdsource to the community. If you see rogue apps in your environment and you think that this is something that could be seen from other environments that fall into that less prevalent bracket, but might also exist elsewhere, contribute. We have a repo for it. I have it linked here, QR code. I promise it's not sus. But yeah, and we have like examples like we walked through earlier of like EM client. There's a couple more out there. But yeah, just you can raise an issue and contribute to this.
It's just a library of techniques, tactics, and procedures observed during OAuth attacks, right? So it's just a place you can go to learn a little bit more about like what apps are used in which attacks. And yeah, if you've seen one and you don't see it on that list, please put an issue in the GitHub or open a PR or something like that. All open source, all community driven, all community led, just to enrich everybody's understanding about what these attacks actually look like. Because I don't think like many people, a lot of people, like everybody knows phishing. Everybody knows like, I shouldn't like punch my credentials into some weird URL, but like this one's weird because in the social engineering context, you might be given a link that leads to Microsoft's actual authentication infrastructure. In that case, if you've been trained to look for weird links, you're going to see login.com, .microsoft.com and be like, oh, this is probably safe. And you might fall victim to one of these kind of consent grant attacks, right? So, yeah.
I'm just grabbing the GitHub link to throw in the chat. There we go. So check it out. Yeah. And then what else do we have? Okay, so limits and constraints in terms of this POC. Like I said, and Matt called out, we built this out about 2 months ago. So like as a first iteration, this is great, being that we're just diving into the unknown with this. And we were really able to take away a lot of ideas and like a sound methodology for how we can actually find rogue apps out there and what we can do about it. So this was really helpful in encompassing 10% of the data that we have visibility into. One of the constraints was like with the ETL bottlenecks of like loading this data in, since we're pulling from the Graph API, to no fault of the Graph API, but it took a while. It is slow, like, so, I mean, there's ways that like we tried to speed it up, doing like multi-threading, having beefier processor, having it on like a dedicated EC2 instance to do the data collection. So we did a lot of those good best practices because that's like more my jam, being on like the dev side of the house. But unfortunately, we still ran into that. And I think continuing to work on this and scaling it up, that's something that I'll probably have to like refactor. So fun. And then looking ahead, like I said, being able to take in more data from the Graph API, getting it into Neo4j. To Elasticsearch was like super easy with like bulk ingestion. So that was quite snappy. But yeah, I think being able to like scale this POC to something more tangible and with a larger data set, might have to like refactor data model. Like, does it make sense? And having maybe a more systematic way of delving into Neo4j, because we got to the point of like eyeballing data in Neo4j, and we had some helpful queries that we could reference to say, hey, run this query. Like, I think we have like a doc, or I have like an Obsidian note of like various queries for Neo4j just to peel out some of the more interesting and anomalous relationships, but those can easily be teased out. So yeah, that's all we got for you guys. And like I said, final takeaways. I feel like I kind of touched on most of these already, but for safeguarding against rogue apps, MFA, make it more difficult for the attackers to get in the first place. Secondly, no shadow IT. Obviously, we do not want admins, we do want admins, if they can be proactive about managing user content to apps and M365, that's key as well, so that normal users are not creating apps left and right. And then that's how we end up having all these separate apps and things spin up and not tracked. And additionally, reducing the attack surface. I know this is more of like a box ticking auditing thing, but but it is really helpful to find or to mitigate any attack surfaces that exist. So any unused apps, being able to audit apps on a routine basis, whether that's like your IT or internal security teams saying, hey, this app hasn't been used in a while and this person has all these permissions. Also, not over permissioning apps, again, principle of least privilege. And then also checking if the app is from a verified publisher and reputable source. So those are all the box ticking things, but it still helps reduce the attack surface altogether. And like we said, we have our rogue apps repo, so you can share what you know with the SMB community at large. That would be super. And we both check it out regularly, so super stoked to see any additions to it. And yeah, so just to wrap up, quick acknowledgements. We both wanted to say thank you for Dave. I know we gave a shout out earlier, but thanks again, Dave, for getting us started with app credentials and starter code for when it came to the Graph API and all of your knowledge of Microsoft things. I am still very much learning, but super helpful, and appreciate all the time you've given to us for that. I also wanted to give a special thanks to Sharon Martin for writing the initial Huntress blog post. If you look back maybe like about a year and a half ago, I think it was August 2023, she wrote one on legitimate apps as Traitorware for persistent M365 compromise, which is like, when I learned that when we were doing this POC a couple months back, this was all like zero to hero knowledge for me. And the fact that Sharon had written this out like over a year back, and I'm just having like a mind blown moment. Like, she's just a rock star, and really appreciate her intel from that blog. Definitely check it out if this is your jam. Really helpful and informative and really trailblazing. And yeah.
So thanking Dave specifically, Dave handed me the credential for the Huntress identity app, effectively giving me access to every tenant that Huntress controls, and said, Matt, I'm going to give this to you, but like, this is literally the most dangerous thing I've ever done in my career. And I was like, got it. I won't let you down. So just thank you for that trust, Dave. That enabled
that totally wasn't nerve-wracking.
Yeah. I'm using that credential to authenticate as the kind of doing what I'm like, the irony is not lost on me that I'm about to do the thing that we're studying attackers do, is authenticate as the application and then access resources on their behalf. So I'm like, the irony is not lost on me. Thank you, Dave, for that. It unblocked the research and it led us forward into the unknown.
Amazing.
And then I think we got our next Tradecraft Tuesday. We've got our predictions for 2025. That's after the new year. We don't quite have the lineup for that one, but we know the subject. We're going to be talking all that ragtime about, what we predict in 2025. A lot of cred stealers, a lot of ransomware. A lot of people are going to lose a lot of money probably. But stay tuned for that. But this is the last Tradecraft Tuesday of the year. So I just wanted to say thank you all for tuning in. We'll see you after the new year. Thank you to Christina. You absolutely killed it for your first Tradecraft Tuesday. So congratulations. And
thank you.
Yeah, everybody. I mean, we answered a couple of the questions along the way. If you do have any questions and we didn't get to answer them, just go ahead and reach out to us. Our emails are on the board there. Take care of yourselves. We got 1 minute to the top of the hour. Nope, it's the top of the hour. There we go. Take care of yourselves. Take care of each other. Happy holidays. Happy New Year. We'll see you in the new year. And bye.
Thanks all. Bye.